Welcome to our presentation on the DC-SCM 2.0 LTPI interface. LTPI stands for LVDS Tunneling Protocol and Interface. My name is Kasper Wszolek. I'm a principal engineer working on manageability solutions for Intel server platforms. I'm here with Zeng, who is a principal engineer responsible for hardware architecture of Intel server platforms. In this presentation, we will provide you with a background of the previous solution you can find in DC-SCM 1.0 and why are we replacing that solution with LTPI. We will go through LTPI introduction and provide a description of the channels concept. We will go into working principle details to show how the LTPI logic works. We will provide a definition of the frames and electrical I/O specification for LTPI interfaces. We will provide a description of the link training procedure and how the interface is brought up. And we will end the presentation with an example of the real implementation of the LTPI interface. The DC-SCM modular design puts a lot of platform components onto the module itself, such as BMC, root of trust, front panel, SPI flashes, DPM, and so on and so forth. And this brings a challenge of moving all the interconnects that are needed for those components onto the module itself. The biggest limitation is the DC-SCM connector that we use. This is SFF TA1002 for C+ connector. That is limited with 168 pins. This problem has been already solved in DC-SCM 1.0, but by the introduction of two serial GPIO interfaces that are utilizing 9 pins. Those interfaces are used to tunnel GPIO signals between the HPM platform and the DC-SCM module. But the SGPIO is limited to tunneling only GPIO interfaces. With LTPI, with the DC-SCM 2.0 LTPI, we introduce high-speed scalable interface that is using low-voltage differential signals and is providing higher bandwidth and possibility to route to tunnel not only GPIO interfaces but also other low-speed interfaces like I2C, UART, SMBuses, or OEM extension as well. The LTPI interface is primarily used to tunnel physical interfaces between the DC-SCM module and HPM module. Its primary function is to connect the physical interfaces between the BMC, such as the GPIO, I2C, UART, some OEM extensions, with the physical interfaces on the HPM that are either connected to the physical devices on the platform, such as CPUs, PSUs, sensors, and so on and so forth. And LTPI allows for utilizing two CPLDs on the DC-SCM module and on the HPM module to tunnel all those interfaces with a high-speed interconnect based on LVDS interface. With LTPI, we introduce a concept of channels. So each of those physical interfaces that is serialized through LTPI is allocated a portion of the LVDS bandwidth. Each of those interfaces is defined by its own channel. Each of this channel is being tunneled through the LTPI interface with a predefined and pre-allocated bandwidth. By bandwidth, we mean here the number of bits that are allocated for each of this channel on the LTPI interface. On LVDS side, the LTPI interface is using a known concept of time division multiplexing, which means that each of those channels will be sampled and tunneled in a respective number of bits on the LVDS interface. With LTPI, we define a GPIO channel I2C channel, UART channel, OEM extension, and data channel. And only GPIO channel is required in order to be compliant with the specs. All the other channels are considered optionals. The working principle of LTPI can be shown on this simplified diagram of the logic that is running on DC-SCM CPLD and HBM CPLD respectively. Those are the same blocks, the same logic IPs, just mirrored between each other. So what we can see here is that there are some physical interfaces on the DC-SCM module, like I2C, GPIO, UART, that are typically connected to the BMC SoC that is located on the DC-SCM part. Now those physical interfaces are being captured. The traffic from those interfaces are being captured by the dedicated interface controller located in the LTPI logic in the CPLD itself. Then those interfaces are being put into the LTPI frame. The frame is generated together with a checksum that is associated with the captured state of those interfaces in the frame. Each of the interface, like in this color coding here, is denoted specific fields in the LTPI frame. And the more bits each of those interfaces is allocated, the more bandwidth actually is being allocated to those interfaces. So as you can see in this example, there are low latency and normal latency GPIOs are allocated a portion of the frame. The I2C interfaces are also allocated another portion of the frame. Then the UART and OEM extensions and data channels. When the comma symbol is being added, then the LVDS PHY interface is being used to serialize the frame into the LVDS link between the DC-SCM and HBM. On the other side, in this case on the HBM side, the LVDS PHY is being used to capture the frame from LVDS serial link and put it into the internal FIFO buffer. From this point, the comma detection logic is analyzing the frame and is identifying the beginning of the frame by looking for the respective comma symbol. And after decoding, the frame is parsed and checked against the CRC error. And if it's correct, then it's all the states from that were captured on the DC-SCM side are being reconstructed on the HBM side on the respective interfaces as well. So what was the captured as a GPIO on the DC-SCM side is now being reconstructed on the respective GPIO on the HBM side. And on the HBM side, those interfaces are connected to specific devices like CPU or power supply unit or any other device that utilize those links. Now the other direction from HBM side to DC-SCM side is following exactly the same principle. When it comes to frame definition, we in the DC-SCM 2.0 we define the frames to have a constant length. This gives a lot of benefits of controlling the link, but also it provides a predictable latency on the interfaces, regardless how much bandwidth of this frame is being used. And the frame is constructed with 16 symbols. The first symbol is the comma symbol, and then there is a payload that can vary between the implementations depending whether implementation wants to have more GPIO allocated in the frame or more I2C links or even OEM or data channels. And at the end of the frame, there's a CRC checksum. LTPI frames are being identified by the specific comma symbols. Right now we have defined 3 separate comma symbols that are being used to move in the bring up sequence of the LTPI interface that we will go into more details in the following slides. But the first group of frames is used to detect the link and select the speed of the link, the target speed of the link. The next symbol is being used to advertise the capabilities and to move to a configuration and acceptance state where the link is actually selecting capabilities that are supported by both sides, by the DC-SCM CPLD and HPM CPLD. And the last frame is an operational frame that once the link is brought up, it's being constantly used as the operational frame. Now Roy will talk about the electrical specification of the LTPI and the LTPI bring-up sequence that we defined in DC-SCM 2.0.
The LTPI using a LVDS-based electrical interface. So we have defined the voltage level, differential voltage swing at the DC-SCM connector side with minimum of 100 millivolts up to 800 millivolts max. The LVDS, we are using an AC coupled LVDS spec. The major purpose is trying to adapt to different voltage level on the TX and RX side. By using the 0.22 microfarad of DC AC coupling cap, we allow the TX side running at 3.3, 2.5, or 1.8 at different implementation of LVDS. And similarly, the ARC side can run at an independent voltage level as well. So this allows the maximum compatibility with the current devices such as PLD and PGA available in the industry. So from the whole link perspective, we are going to support up to 8 pins with 2 TX, 1 TX plus 1 clock as a TX pass from HBM to the SCM. And then we have another symmetric pass from the SCM to HBM. From the whole link perspective, we specify that AC coupling cap should be placed on the DC-SCM side with PCB impedance of 85 ohms and termination resistor of 100 ohms. The whole LVDS LTPI supports 6 states on the link training. The first 2 called link detect and link speed. They are running at the base frequency in order to help both sides to detect and train to a maximum agreed frequency called the target frequency. Once they have reached the target frequency, then the state machine will go to the advertised stage in order to communicate both sides about the maximum, about the capability that supports from both sides. And once advertisement was done, then the SCM and HBM will go to the different states. SCM will go to the configuration state to allow to tell what's the expected configuration that HBM would like to, SCM would like HBM to set. Once HBM accepting that configuration, the both state will go to the link 0 state to go to starting the standard operation. At L0, once there's any link error or there's a physical reset, the whole state machine can be restored to the link detect states and go through the whole training sequence again.
Thank you, Roy. Right now, we will go through an implementation example that we did of the LTPI interface interconnecting to DC-SCM modules that you can also see in our demo that we show in an experience center. So we've been using the Intel Max 10 10M25 CPLD with an LVDS link running at 200 megahertz. In this implementation, we implement tunneling of 112 normal latency GPIOs with 4 low latency GPIOs. We tunnel 4 I2C links and 2 UART interfaces. We are not using the entire bandwidth of the frame in this implementation. There's some fields in this 160 bit frame that is not being utilized in this example implementation. The point is that what we wanted to show is the latency and bandwidth of the interfaces when they are being tunneled through LTPI interface in DC-SCM 2.0 implementation. For the normal latency GPIOs, you can observe that the logic itself and the LTPI interface is introducing around 9.4 microseconds of the latency for the normal latency GPIOs. For low latency GPIOs that are allocated the dedicated bits that are always transported in every frame through the interface, the latency that is being introduced in this implementation for those GPIOs is only 1.3 microseconds. On the I2C links, which are running from the BMC perspective at 400 kilohertz, due to the latency introduced by the LTPI interface, the actual interface speed is reduced to 112 kilohertz. But it's following the principle of clock stretching, and from BMC perspective, this is behaving according to the spec. From the UART links perspective, there is no drop in the bandwidth, so the interface running at 115,000 baud is still running at the same speed on the other side of the link. However, latency is introduced to this communication that does not have effect on the actual bandwidth of the interface. From resource utilization perspective, you can see that this implementation is utilizing a total of 2,200 logic elements from the max 10 CPLD that we used. But if you look closer, the actual logic that is responsible for GPIO, LTPI interface management, state machines, and those basic channels that are always required, like GPIOs, is only consuming 1,000 LEs out of the total logic elements consumption. The I2Cs that we also support in this implementations are utilizing the logic that is responsible for I2C tunneling is utilizing 1,200 LEs. And in this implementation, each of the supported I2C links is consuming 300 LEs per link, so it's easily to estimate how many LEs will be required on the Max 10 devices for supporting those interfaces. We would like to recap the key features of the LTPI interface. So first of all, this is based on LVDS-IO, which has improved signal integrity and much higher bandwidth comparing to single-ended interfaces. And also it's a pretty popular interface supported by most of the CPLDs and FPGAs available on the market. The LTPI also defines the AC-coupled interface, which allows for use of multiple LVDS voltage standards. And this way it improves interoperability between different DC-SCM implementations that are utilizing different CPLDs or FPGAs to implement this link. We support also multiple interfaces, not only GPIOs as it was supported in DC-SCM 1.0. We introduce the support for SMBus and I2Cs, UARTs and data channels, and also leave a space for OEMs to provide their own extensions. The interface itself is in the reference design that we are showing. It's running at 200 megabits per second. But the latest FPGAs on the market, you can easily reach over 1 gigabits per second on the LVDS pins. We also believe that the interface is scalable and flexible for the future solutions, for OEM extensions, and also the data channel that we define in the specification can be used to pass the raw data between the HPM and SCM CPLD, allowing for random access interfaces from the BMC or any additional extensions utilizing standard data buses that are being used in the CPLDs or FPGAs like Avalon Multimaster or Wishbone interfaces. From interoperability perspective, we define link training and capabilities exchange protocol that allows to negotiate between the DC-SCM and HPM the desired configuration of the link, the final desired operational speed, and also allows for BMC to make a decision which of the tunneled interfaces are being enabled and what is the configuration of the link that is being brought up. With that said, we encourage you to join us in the Virtual Experience Center, where we show a demo of the LTPI interface that is running on Intel Max 10 CPLDs. We also encourage you to see the demo of LTPI implementation provided by Lattice Semiconductors that is running on Lattice Mac X03 FPGAs. In case you have any feedback for us, please reach out through the hardware management module subproject through the wiki mailing list or directly over email. Thank you for your attention.